Okay, hello everybody. So here we have a vector field, and we have a curve, which is a helix, sort of wrapping around as it goes up. Oop. And it's just going from one point to another point. So first let's just make sure we understand this notation. This vector field sends x, y, z to zx, zy, comma, all these commas, x. This is k hat, j hat, I hat is just the first, second, and third components. And so this is the map F. And I'm going to drop this little arrow because we don't need it. And then over here, this curve, this helix, is, well, let's call it G. And what does G do? Well, it maps T. The map G sends it to the point cos T, comma, sine T, comma, T. So, I mean, for example, it sends the point t equals 0 to cos of 0 is 1, sine of 0 is 0, and then t is 0, okay, so at that point. And it sends pi, because look at that, see there's the pi there. And okay, what's cos of pi? Yes, it is -1, and sine of pi is 0. Okay, so, and in particular, if we can visualize this curve in three-dimensional space, it starts at 1, 0, 0, which is here. This is g of 0. And then it goes to -1, 0, pi, which is back here, and then up by pi, maybe up here, g of pi. And it goes by circling in the xy plane as it's rising in the z. And so it sort of loops around and up like that. Okay? Okay, so this vector field here, F, it assigns, I mean, let's make it blue in our picture. It assigns some vector to every point in space. In particular, all the points on the curve get vectors. And, you know, we don't really know which direction those vectors are pointing unless we really plug in. But that's the vector field F, and sometimes they like to write a little arrow over it. Okay, so we need to compute the work. And the work says, you know, how much is the vector field F going along our curve overall as we go all across the curve, you know, average the amounts of F that are going along the curve, okay? And so let's write that down in words maybe. So the work integrates some function along our curve. What function? Well, it'll be the dot product of the vector field with the direction of the curve. Along our curve will be the unit tangent vector. So unit tangent vector. And this dot product says how much are these two vectors pointing in the same direction or opposite directions. Will be if this dot product is positive or negative, or if they're at 90 degrees, if the vector field is 90 degrees to the tangent vector, then it'll be 0, okay? And so this is the function on the curve, but we'll write it out in more detail. But in more detail. Okay, so let's do another picture. Here we have, well, we're going to go from 0 to pi. So I guess, well, here, maybe I'll make it dotted. And then t equals 0 to pi. That's our t-axis, and it's going to be mapped into space to become our curve. That sort of wraps up here. Okay, that's g of 0, g of pi. And then we actually have the vector field, which maps to R3. And then we're going to want some function, let's say h, that maps to r, and h will be this dot product here. And this is the function we're going to integrate over the curve, and we'll do it by pulling it back to integrate from t equals 0 to t equals pi, and that will be an easier integral. Okay. So first, let's compute the change in volume factor. So, because we're gonna, G distorts volume, in this case, one-dimensional volumes, which is length. And so we need to compute the change in volume factor, and that is going to be the square root of the determinant of the gram matrix of, well, this thing. So let's compute the derivative of G. And let's say, we'll just, G has one input variable, so we'll just sort of take d dt of this. Okay, so you see it up here? Cos becomes minus sine becomes cos, and t becomes 1. Okay, and then, so that's from taking the derivative, and now I can compute the gram matrix, which is just a 1-by-1 matrix. Well, it's going to be sine squared plus cos squared plus 1 squared. And, this will be a 1, and so we get 1 plus 1, and that is 2. Okay, and then I take the determinant of a 1-by-1 matrix, gives me just that number, and then the square root gives me the change of volume factor is the square root of 2. Okay, so maybe I'll put this, all these formulas are in a little thought bubble because I know that, instead of integrating over this difficult curve, I'm going to integrate over a nice rectangle, a one-dimensional rectangle from 0 to pi. Well, I got to pay a price to distort volume. Okay. Now, what is this function, this dot product? Okay, so let's take that, and what we really want to do is we're going to integrate some function that takes the vector field and the unit tangent vector. And so let's compute f after g. Okay. So first let's just remember what g does. G takes t and send it to cos t, sine t, t. Did I get that right? Cos t, sine t, t. Yes. And then f, the vector field, takes x, y, z, and spits out, I think it was zx, zy, and x. Let's check that. Zx, zy, x, right? Zx, zy, x. Okay, so then I can compose these functions and get, okay, zx becomes t cos t, zy becomes t sine t, and x becomes cos t. Okay? So I want to take the dot product of the vector field with the unit tangent. So let's take the dot product of the vector field with the unit tangent. So what's the unit tangent? Well, that's going to be g dot of t divided by the length of g dot of t. And what's g dot of t? Well, actually, we already computed it, right? Here it is. It's really w1. It's going to be w1 divided by the length of w1. Well, we already computed the length of w1, and so that's going to be 1 over the square root of 2 times minus sine cos 1. The vector minus sine cos 1. Okay, so that was a lot. but we had already done it over here, okay? And so now if we take the dot product of the vector field, remember, here's our vector field, and I can put it in the t variables by composing the functions. And I'm going to see how much does the vector field point in the same direction as the unit tangent vector. So at any point here, I have a unit tangent vector, and I have the vector field, and I'm taking their dot product to see how much they point in the same or opposite directions. Okay, well, I can take the dot product of two vectors. So this dot product is going to be minus sine t times t cos t. So let's keep the 1 over square root of 2 outside. And then I take t cos t times minus sine. Oh no, not comma, plus. I'm taking the dot product of two vectors. So I need to add up their products. So now t sine t and cos t. That looks good. These are going to cancel. Plus the last one, 1 times cos. And then this 1 over root 2 just sort of is going to wait and stay outside. And this cancels this, giving a 0. And the whole thing is 1 over square root of 2 times the cosine of t. And so this right here is the function that we're going to integrate, this dot product. So let's do that. To integrate this function, we need to take into account the change in volume factor. So the integral from t equals 0 to t equals pi of the function, well, let's see, this times the change in volume factor. So that's square root of 2 was the change in volume factor up here. And that's going to cancel this one. And then the cos t. And so now we see that this is going to be a really easy integral. T equals 0 to pi of the cosine of t. So what differentiates to cosine of t? Let's call this function little h. Then big H is sine t. And you can check the derivative of this will give this function. Okay, so I do h of pi minus h of 0. Sine of pi is 0. Sine of 0 is 0. And amazingly, this integral is 0. So that means that as this curve is winding up through space, this vector field is pointing in all these different directions, but overall, the amount that it's going along the curve and the amount that it's going against the curve cancel out exactly. And so the overall work of moving along this curve in this vector field, sort of a force field, is 0. Okay. So this is an interesting problem. It really requires you to remember what are the dimensions, where are these maps going, and so this picture is incredibly helpful to see that really on the curve we have the vector field and we have some other function which measures how much the vector field is pointing along the curve. And yeah, it's pretty interesting. So really this function h is this function. And you see that the vector field has to go in to create the function h, which we are eventually going to integrate over the curve by integrating this composed function. In other words, everything needs to be in the t variables. And so that's why our dot products are all in the t variables.